our last spotlight session of today. It's my pleasure to kick off the session. Jinglong is going to present some recent work. Jinglong, you can share your slides now. The talk is on Pigeonhole design, a new approach to experimental design. And our discussant for the first work is Chen. During the presentation, feel free to ask your questions using the chat. There will be time after the talks to have a discussion on this. Jinglong, thank you for your paper. The floor is yours.
Thank you so much for the introduction. All right, and thanks everyone for coming. So my name is Jinglong. I am an assistant professor at Boston University. This is a joint work with Zijie Zhou, who was a undergraduate student at Purdue University when I was a PhD student at MIT. And then, so both of us graduated. He's currently a first-year PhD student at MIT working with Zijie and Patrick Jallet. And I started my career at Boston University. So this work I'm gonna present today is entitled Pigeonhole Design, which is a method to balance the sequential experiments from an online matching perspective. So let's start by thinking about when people are running experiments, what would people do? So think of a randomized experiment. The most naive way to run such an experiment is to maybe put people into a treatment group and some other people into the control group, randomly assigning half of them into treatment, which we denote using the group B, and control, which we denote using the group A. So this is the gold standard when you're running an experiment, or A/B testing. That everybody would like to do this, and that has been widely adopted in practice and widely studied in the literature. So when we're running experiments, one challenge that we will usually face is that the experimental units are typically heterogeneous. So think of this following example. Maybe in our platform, some of the users that you run experiments with, they wear different colored hats. They wear different colored pairs of glasses, and they wear different colors of pants. When this happens, and when you believe that these covariates are important to the observed outcomes, then you should try your best to balance the users in your treatment and the control group. What do we mean by saying a balance? So here is an example. If we carefully select 4 of the users into the treatment such that exactly 2 of them wear this red hat and exactly 2 of them wear the blue hats, then this is what we call a balance in their covariates. And as you can see here, we see a very nice balance in the sense that exactly there are 2 people who wear a blue hat versus a red hat in both the treatment and control group, and so it does with the color of the glasses and the color of their pants. So this is all good. So people have studied this balancing in experimental design for so many years. It is widely adopted in practice as well and well understood in the literature. And the challenge that we're trying to address in this paper is, what if the experimental units are not revealed to you at once? What if they arrive sequentially? What does it mean? When the first user arrives, you do not know the remaining users. And you must put the first user into either treatment group or the control group. Because when a user arrives at your online platform, you either have to show a particular color of the button to this user or a different color to this user. So you must make the decision in an immediate way. So when the first user arrives, this is less of a problem because we can always randomly put the first user maybe into group A. But when the second user arrives, we have to face a decision of whether we should put the second user into the same group or into the different group. If we believe that the second user is wearing a blue hat, which is of the same color than the first user does, then to some extent, we would love to put the second user into the opposite treatment version, so that in both groups, we now have one user who wear a blue hat. But on the other hand, if you really believe that the color of their pair of glasses is more important, then we would love to put the second user into the same version of treatment so that we have enough variability in the same treatment group that has one black pair of glasses and one golden pair of glasses. So how same are same and how different are different? So this is the question that we're trying to address here in this paper. And we're trying to provide a way to formalize this question and to answer this question. So let me pause here for maybe 5 seconds to see if there are any questions. Because this is a one-slide summary of the whole paper. Wanted to make sure that the motivation is super clear so far. All right, cool. Before we move on to the details of this talk, let us zoom out and look at this high-level picture. So we're going to answer this question from an online matching perspective. And we talk about matching. Different people from different fields, they have different understandings about what is matching. If you're asking people from statistics, when we're talking about matching, then the first thing that comes to their mind might be a matching estimator. Among many common estimators, like if you do regression adjustments or so on and so forth, then this is one very practical and simple way of coming up with an estimator. But if you ask somebody from our OR community, then we might think of matching as an algorithm. For example, a lot of people are working on online matching algorithms with trying to analyze the performance of different online matching algorithms. So the punchline of this work is basically to take the online matching perspective to try to answer some questions that people would be curious about who are more familiar with the matching estimators. So in this talk, I'm going to first introduce a version of the online blocking problem, which is the question that we're trying to study. And then we're going to introduce the pigeonhole design, which is an experimental design method that has a provable guarantee on this online blocking problem. And then we're going to compare two benchmark designs, the match pair design and the completely randomized design, to analyze how good or bad does the different designs perform. So here are a little bit of notations. Let's consider a discrete finite number of users who arrive in a sequential way. Let there be capital T users. Capital T is known to you and fixed at the beginning of the horizon. So typically, if you think of an online platform, then a typical experimental budget could be super big, like 100,000 to 1 million. Or if you think of a sequential clinical trial, then in this example, maybe the total number of volunteers who come to your clinical trial is going to be much smaller, maybe at the scale of 100 to 1,000. And we're going to say that each user, which we use this, which is indexed by letter T, is captured by a p-dimensional covariate information. And we normalize it to between 0 and 1 bounded, but this is sort of without loss of generality. So in this paper, we model the XT, the covariate information of all the users, to be adversarially chosen. Of course, if you have prior historical data, then you can estimate the stochastic distribution. You can definitely do that. But just like in this paper, we think that adversarial rival sequence might be easier to analyze in some sense. We distinguish two cases. The first case, which we refer to as a single dimensional case, is when the dimension is only of single dimensional. And for example, in online platforms, maybe there is a very highly predictive KPI, such as browsing type, that can predict the click-through rates. In some other cases, when there are more than one single covariates, we refer to as multi-dimensional case. And this captures the more common cases where people have user demographics, like their age, their gender, and so on and so forth. So the treatment assignment for user at time t has to be immediately determined when the user comes to our platform, because you must show the user something, either a blue button or maybe a green button. This usually has to be done within 10 milliseconds. So when you make this decision, you typically do not have the chance to accumulate enough users for you to make a delayed decision. And we refer to user T assigned into the set A as being assigned into the control group. For example, this could be the old S display, maybe in color blue, and we say that T belongs to B, the treatment group, if it's a new advertisement display. And here's the constraint, which is that we must put half of the user into treatment and half of the users into control, which is an omnipresent constraint that people enforce in the discrepancy theory or in this experimental design with covariate information. And we're trying to adopt the following objective, which is to minimize the discrepancy between the treatment group and the control group. How do we define a discrepancy? For each pair of users, T and T prime, we define this pairwise discrepancy simply as the L2 norm on the covariate space, this Euclidean distance between these two users' covariant information. And for two groups of users, we define the minimum weight perfect matching as the total discrepancy between these two groups of users. So basically, we're trying to find, after we have a treatment group and a control group, we try to find this one-to-one paired matching such that when we sum up the weights, sum of the pairwise discrepancies together, the total sum of the discrepancy is minimized. And we can always find a total discrepancy for each partitioning of the treatment and control group. So each partition corresponds to one discrepancy. And if we maybe change some of the users between these two groups, then this comes to a different partitioning, and this will lead to a different total discrepancy. And our objective is trying to find a partition that minimizes the total discrepancy accumulated. So if this problem is given to you, then this is an assignment problem, which is super easy to solve. But we're trying to solve this problem in an online sequential fashion. So here's an illustrating example in this single dimensional space. Let's suppose that group A has two users, X1 who arrived on the first period and X3 who arrived on the third period. And they have values 0 and 0.5. And let's say that group B has two users whose covariates are 0.7 and 1. Then in this case, what is going to be the discrepancy? We're basically trying to find the two pairs and trying to sum up the weights on these two pairs, which is going to be 1.2. So if you are quick enough, then you might immediately ask, why should we stick to this particular type of partitioning? Maybe if we exchange X2 and X3, exchange these two middle users, then we could probably end up having a smaller total discrepancy, which is as small as 0.8. So this is what we're trying to do. We're trying to find the assignment that is going to lead to a very small total discrepancy. And we're trying to do this thing in a sequential fashion. So there are three questions that might come to our mind. The first question is, if all the user covariates are all known in advance, how to optimize, how do you do this partitioning, how to do this blocking? The second question is, if you do not use any of the covariates, but if you just only randomly do the treatment and control partitioning, then how bad is going to be the discrepancy? And the third question is, if all the covariates are sequentially reviewed, then what can we do? Which is the primary focus of this work. So let's start by answering the first question, which is, what if all the user covariates are all known to you in advance? Then we're basically trying to solve this, the following minimization problem. And we refer to a match pair design as the design that first solves this minimization problem, and then assign treatment and control based on which user goes to group A and which user goes to group B. So in the single dimensional case, the above problem is very easy to solve. Why? Because after you see all the user covariates, you can just focus on this single line and match the two adjacent users in pairs. And this is what we're trying to do. For each pair, you randomly put one of the user into the group A and the other user into the group B, so that you have a very nice pairwise matching among all the T users. And we can show that this match pair design in the single dimensional case has a total discrepancy smaller or equal to 1. This is a simple warm-up example. It does have a very good performance because the total discrepancy does not scale at all with respect to the total number of users. But it does require all the users' covariate information, which is not feasible if you're in this sequential decision-making setup. On the other hand, what if you do not use any user covariate information at all, but instead we just randomly put users into treatment and control? So this is a feasible algorithm in this online setting. And this is a well-known design, which people refer to as a completely randomized design, which is as follows. We know that there are capital T users, and we're going to randomly select half of the indices to be the treatment users. And if one user arrives, and if this user happens to have an index as a treatment user, then we do treatment. On the other hand, if it happens to be control, we do control. Here's an example. Let the 4 users arrive sequentially. And with probability 1/6, then you're going to put user 1 and 2 into group A, and then 3 and 4 into group B. With probability 1/6, you're going to put users 1 and 3 into treatment, and 2 and 4 into control. And with the last 1/6 probability, then you could put users 1 and 4 into the treatment, and 2 and 3 into control. And with the other 1/2 probability, you just flip the label of the treatment and control. So everything is symmetric. In this case, then we see that the total average discrepancy is going to be 0.93, which is bigger than this 0.8, which is the best thing that we can ever hope for. So we can show that in this single dimensional case, the completely randomized design has an expected discrepancy on the order of square root of T. So now let's do a recap. First, we analyze the match pair design, which is infeasible because it uses all the users' covariates, but it does achieve a very small discrepancy. On the other hand, the completely randomized design is a feasible design, but it does not use any user covariate information at all, and it has a large discrepancy. So is there something in between that we can design? The answer is yes. So let's first pause here for 1 second, and let's review what was the intuition. So the intuition that ensures that people can be matched into pairs is basically that whenever possible, we try to match people in pairs. Whenever we see a chance, we would love to match people in pairs. But the challenge that arises is that we do not know what are the user covariates before they even arrive. Well, wait a second, where are these user covariates? So when we really focus on the user covariates, why don't we start by partitioning the user covariates? Then we care about whom to match to who others. So the first stage that we're trying to do using the pigeonhole design is to partition the covariate space into smaller subspaces. And we refer to each subspace as one smaller pigeonhole. As users arrive at each pigeonhole, we sequentially match them in pairs from within one single pigeonhole. For example, the first user arrives. Let's say the first user comes to the first pigeonhole. Then we randomly put this user into, say, group A. And then let's say the second user arrives. we know that the second user arrives at the last pigeonhole. So there has been nobody who has previously arrived at the last pigeonhole. So we randomly treat this user by maybe one realization of the treatment, maybe putting this second user into group A. And then the third user arrives. We notice that the third user belongs to the first pigeonhole. There is already one user in group A from this first pigeonhole. So now we deterministically put the following user, put the third user into the opposite group, which is group B. And then the fourth user arrives. The fourth user comes to the first pigeonhole, but there is already a pair. There's nobody remained to be unmatched in the first pigeonhole. So we again randomly put the fourth person into either group A or group B. So let's say in this case, the fourth user is randomly selected to be going into group B. And then we continue doing this. Whenever we see an unmatched user at the same pigeonhole, we match it. And when we see nobody being unmatched, we randomize. So the fifth user arrives. There's nobody from the third pigeonhole unmatched. So we randomize. And let's say the last user arrives, and then we match it to the fifth user who belongs to the same pigeonhole. And this is a high-level idea of a pigeonhole design. So the key idea of the pigeonhole design is that users who have the similar covariates are matched in pairs from within each pigeonhole. And those users who have different covariates are independently assigned. So let's formally define what is a pigeonhole design. So a pigeonhole design takes two inputs. The first input is a partitioning of the covariate space, which we refer to as a pigeonhole. In this example, let there be 4 time periods and let the 2 pigeonholes to be 0 to 0.5, including 0.5, and the second pigeonhole starting from 0.5 to 1. And also a pigeonhole design has a second input, which is beta, the balancing parameter. So let's say, for example, the balancing parameter here in this case, beta is equal to 1/4. I'll explain how does a balancing parameter work. So, but before I explain how it works, let's follow me with this example. When any user arrives, if we know that this user is the first several periods before the balancing periods, then we run the pigeonhole design by first finding the pigeonhole such that this user belongs to. And second, if there are even number of users that have already arrived in this pigeonhole, then we randomly assign treatment or control. For example, here x1 is equal to 0. There's nobody from the first pigeonhole. We randomly put the first user maybe into the group A. And then the second user arrives. Let's say the covariate is 0.7. It belongs to the second pigeonhole. There's nobody here in the second pigeonhole, so we randomize again. Let's say we randomly put this user into group A again. And then if there is an odd number of users from this pigeonhole, then we assign to the group with fewer users. In this case, the third user arrives. The third user belongs to the first pigeonhole. There is only one user here, so we deterministically put the third user into the opposite group, which is the group B. And this is the end of the randomizing periods. And lastly, during the balancing periods, then regardless of the user covariates, we put the user into the group A or group B that has a fewer users. So we ignore the covariate information and do purely balancing, balance the number of users in group A and group B in this stage, in the balancing stage. And the purpose of this balancing stage is to purely satisfying the constraints that half of the users are put into treatment and the other half goes into the control group. So I guess I can take a pause here for a few seconds, just in case there are any questions. There's no, I'm gonna move on to a quick analysis of the pigeonhole design. All right. So the first observation that we make here is that at any time, each pigeonhole has no more than one unmatched user. at any point in time. So this motivates us to think of the following trade-off, which is that a smaller pigeonhole is going to lead to smaller discrepancy from within each pigeonhole. But if there are many unmatched users from so many pigeonholes, then this is going to lead to pairing or matching across pigeonholes, which is likely going to give you a large discrepancy. So there's a trade-off between designing smaller versus larger pigeonholes. And we're going to introduce this parameterized pigeonhole design here. So let's suppose that the size of the pigeonhole is parameterized by t to the negative eta. And then let the balancing parameter be t to the 1/2 of eta minus 1. And then we're going to consider the first t minus t to the 1/2 of eta arriving users. So for those who are matching pairs within each pigeonhole, the discrepancy is going to be t to the negative eta. And there are an order of t many users who arrive during these periods. So we time t with this t to the negative eta. So in total, the total discrepancy is going to be t to the 1 minus eta. On the other hand, there are at most t to the eta users unmatched because there are t to the eta pigeonholes here. For these users, we match them to the balancing users. And the discrepancy is going to be of this big. This is a slightly more tricky analysis, which I will not talk about in this talk today, but it does require a non-trivial coupling technique to couple with the completely randomized design, which we have carefully analyzed in the previous slide. So basically, we use the analysis of completely randomized design to analyze the pigeonhole design's performance in this by matching them across different pigeonholes. So combining two parts, we're going to get a total discrepancy at this big. And if we choose eta to be 2/3, then this is going to give us a small discrepancy at the t to the 1/3. So the story so far is basically saying that we have designed a pigeonhole design that is better than the completely randomized design and worse than the match pair design when there is only one single dimension. And,
so, well, 3 minutes remaining, just one.
Okay, I was about to ask about the time. Thanks. Great. So, when there are multiple dimensions, I'm going to be very quick about the slides. So basically, they follow the exact same intuition, but the mathematical analysis are going to be different. The one main important takeaway here that I do want to emphasize is that in the multidimensional case, even for the match pair design, even for this offline optimal benchmark, we cannot do better than this big. So we're going to solve this slightly complicated optimization problem, but it's still polynomial time solvable. But the solution of this optimal solution, which is the offline optimal solution, is going to give you a discrepancy at this big. It is no longer small. So as a result, all the discrepancies of all the designs are going to be quite big. But we're able to show that the pigeonhole design, it closely matches the discrepancy of the match pair design, as we can see from here. And a second note to make is that the completely randomized design is very challenging to analyze in this case, in the multidimensional case, and we're only able to lower bound the discrepancy of the completely randomized design by the match pair design, but we don't know what is an upper bound because it's difficult to analyze. So let me show you some numerical results. This is when in the single dimensional case, the red curve is a completely randomized design. The green curves are different versions of the pigeonhole design, and the black curve is a match pair design. It does perform very well in the single dimensional case. And in the multidimensional case, as we can see, everything grows larger with respect to t. And when the dimension is very big, for example, 20, then the red curve and the blue curves, they coincide, meaning that there is not a lot of benefit of using a pigeonhole design in this case when the covariate is of high dimension. So in this case, we do not recommend using a pigeonhole design. But I mean, I do also want to recommend that matching in the high dimension is a very challenging thing to do. This is also recognized by a lot of statistics literature. So do I still have 1 minute to do a quick pitch of the this area? Cool. So I'm gonna conclude by giving this pitch about experimental design in the technology companies, which is emerging areas in the current research. So basically, the gold standard of running an experiment or running an A/B testing is to run a randomized control trial, but it sometimes fails in some applications due to either interference or due to heterogeneity. And this is a growing area. And here I would like to point to a partial list of recent works. So when people run user level experiments, one way that people run such experiments is to refer to some structural models. So there is a sequence of works on model-based designs. For example, Ramesh, Hannah, and Gabriel, together with somebody from Airbnb, they have a sequence of works around designing experiments by distinguishing the listing side and the buyer side randomizations. And the second paper, and also they have some recent follow-ups. And also by Stefan and Kwang, and also their follow-up paper, they talk about trying to run experiments under the equilibrium effects. And if you were here in the conference, then Ido, Arthur, and Elon, they have some very recent work that talks about a very cute idea of interpreting the results of an experiment by referring to the shadow price, which is by interpreting the dual space and answering how big is the trimming effect. This is a very cute and very elegant idea. I strongly recommend you to read this paper. And on the other hand, when people run aggregate level experiments, people usually do model-free designs. So depending on the assumptions that people would love to make, people have written several recent papers. For example, in this paper by Ozan, Chen, and Rat, they propose to run cluster randomized designs. Basically, they put different cities into different clusters, and then they randomize at the city level. And I have written some work on the switchback experiments, and also Ruoxuan and Alex, Shang, and Susan, they have this recent work as well that talks about how do you run a switchback experiment, which is that you partition the time horizon and do treatment and control over time. But all the cities are always receiving the same version of treatment or control. And sometimes when you're afraid that a treatment might persist in your system forever, then maybe once a unit receives treatment, the treatment always stays here. Then in this paper by Ruoxuan, Susan, Mawson, and Hito, they propose to run this experiment with staggered adoption pattern. And also, if you would like to make the assumption that only part of the city across part of the time horizon receives treatment, but all the other cities in the prior to a certain duration of time receive control, then this is what we refer to as a synthetic control design. And I have some work on this as well. And also, if you would like to further relax your treatment pattern so that your treatment pattern can be mostly fairly general, then in this first paper, they propose to run double randomized experiments. And in the second paper by Vivek, Siamak, Tianyi, and Andy, they have some recent works using the matrix completion idea to conduct experiments. So again, these are all some recent works. As you can see, the time are all recent times. So this is a growing area, and have to chat more after this talk. So thanks for your attention.
Thanks so much, Jinglong. We are a little bit over time, so I'll turn it over to Chen in the interest of time. In the meantime, I encourage the audience to ask questions to Jinglong via chat. Chen, the floor is yours. Jinglong, can you stop sharing your slides so that Chen can? Thank you.
All right. Okay. Okay. Hello, everyone. Thank you so much for having me here. My name is Chen. And so, first of all, I would like to say congratulations to Jinglong and Zijie for having another very interesting paper on experimental design. And I very much enjoyed reading the paper. So, without further ado, let me first summarize the paper. So in short, the paper studied a very important and practical question, which is sequential allocation of treatment control. And this problem is particularly meaningful if holding the experimental unit is costly, for example, in clinical trials, and in some other instances, it is just infeasible, for example, in some applications for experimental design in online platforms. And in this problem, we have T experimental units that arrive sequentially. And upon each arrival, we need to immediately decide whether we assign this experimental unit to the treatment group or the control group. Okay? And finally, each unit is associated with with p covariates which can be correlated with the outcome of the unit. So what is the goal of the allocation? So we want to have a good allocation such that the treatment and the control groups have equal sizes, and also they are similar in terms of the covariance. Okay? So why we want this? So because later on, when we estimate the treatment effects, we usually compare the outcomes of the two groups. And we want any such difference comes from the difference of the allocations rather than from any statistical difference of the covariance of the two groups. Okay? And that's why we want these two groups to be similar in terms of these covariance. And in this paper, the authors focus on a very meaningful objective, a very meaningful metric of the similarity of the two groups, which is the total discrepancy, defined as the minimum weight perfect matching of these two groups. So for each unit in the treatment group, we want to have a unit in the control group that have similar values of the covariance. And in the ideal case, the control group is just an identical copy of the treatment group so that the total discrepancy is 0. So that's why this objective makes a lot of sense. And finally, the paper considers an adversarial model where the arrival sequence and the covariance can be arbitrary. And one thing I want to point out is that even if we consider the stochastic model, the problem is still very challenging to solve because this objective is not additive across time periods. So we don't have a DP formulation here. So as Jinglong said in his talk, so here we have two natural benchmarks. The first benchmark is the optimal solution to the offline problem, where all the experimental units are given at time 0. And this corresponds to the classic matched pair design, but it is not feasible to the online setting. And the second benchmark is the complete randomization, which is a gold standard, and where we just simply uniformly at random treat half of the indices to assign half of the indices to the treatment group. And it is feasible to the online setting, but we just ignore the covariate information. So the research question is, can we design better experiments that improves upon the gold standard, which is complete randomization? And especially, can we have performance that is close to the offline outcome? And in this paper, the authors give affirmative answers by proposing the pigeonhole design. So what is the pigeonhole design? So it is very simple. At time 0, we partition the covariate space into blocks with equal sizes. And then in the first stage, which is the first y minus beta times t period, we try to balance treatment control in each block as much as possible. And we do this independently across blocks. Okay? And finally, and for the remaining beta times t period, we just ignore the partition and the covariance information, and we make sure in the end of the experiment, the size of the treatment and control groups is equal to half of the total number of units. Okay. So essentially, I think the high-level idea is roughly you can think of the what we are doing in page 1 is complete randomization within each block, and this is, I think that is a net connection. That's a net trade-off between the match pair design and the complete randomization. And what we need to design for the Pigeonhole experiment are two things. The first thing is the length of the interval, and the second thing is the length of the stage 2. So what is the trade-off in the design? So as Jinglong mentioned, on the one side, we would like to have a fine partition so that we would have a small discrepancy within each block. But on the other hand, we also want to have a coarse partition so that we would have a smaller number of unpaired units by the end of stage 1. So this is the trade-off in the design problem. And how should we design a good Pigeonhole experiment? So here is a rough idea. So by the end of stage 1, for each block, we have at most one unpaired unit, and we know it is independently assigned to treatment or control with equal probability. And then by the central limit theorem, we know by the end of stage 1, the size of the treatment group and the control group only differ by at most the order of square root of the number of blocks. And so we need to reserve beta times t period equal to this amount so that we can make sure we have a balanced partition. And once we settled how many units to reserve for the second stage, the only thing we need to decide is the number of blocks for stage 1. And turns out this is not very challenging to find the optimal number of blocks. So this is roughly the idea of designing the optimal Pigeonhole experiment. Okay. So here is the main results. So first of all, when p equals 1, which corresponds to case that we only have one very important covariant to balance, the Pigeonhole design reduces the total discrepancy substantially relative of the complete randomization, from the order of t to the power of 1/2 to the power of t to the power of 1/3. And what is even more excellent is for the p greater or equal to 2, the performance of Pigeonhole design almost matches the offline optimal. Okay? But on the other hand, we need to admit that when p is very large, the improvement upon the complete randomization is very small. So because the performance of the complete randomization is cannot be worse than the order of t. So the benefit is at most the order of t to the power of 1 over p. So this is basically the summary of the paper. So again, I would like to say it is a very important and practical question to study, especially the literature haven't touched upon too much on sequential design of the treatment control allocation. And also it is very meaningful to examine how much benefit, what is the benefit to design more complicated experiments relative of the complete randomization. And also the Pigeonhole design is very simple and elegant, and it is very promising to extend the design to more general settings that incorporate multiple treatment variants, and also incorporate extend to the case that the treatment and control assignment can be imbalanced. And the paper studied a very important objective, which is minimizing the total discrepancy. But on the other hand, there are some other objectives that can be very interesting as well, especially those objectives that are more related to the analysis step. For example, more related to minimizing the estimation error of some estimator people would like to use in the analysis step. And one related paper is but at all 2020, and there they considered a linear model and they design sequential allocation to minimize the variance of some least square estimator. So I personally think there are a lot of things to do in this part, because sometimes people also incorporate the heterogeneity of covariate information in the analysis step. And in this case, I think it is very interesting to think about, once we incorporate the covariate information into the analysis step, whether there is still much benefit beyond beyond complete randomization. And I don't know the answer, but personally, I'm very curious about it. Okay. And finally, so the paper considers the large P setting, and P is the dimension of the covariate information. And in the adversarial setting, the result of the paper shows that there's not too much benefit relative to complete randomization. But I would say the large P setting is also very relevant in some practical applications. And I feel if we want to say a little bit more in this regime, perhaps we need to assume a little bit more mild assumptions, for example, on the arrival models. And also maybe we need to consider some other performance guarantees, for example, constant ratio analysis or asymptotic optimality, where we have a more preset characterization of the first order term of the performance. Okay? So I have so basically that's basically all I have today. Again, thanks so much for the authors for having a very nice paper, and also thanks so much for the organizers for giving me the opportunity to discuss this paper. It's really the fun pleasure. Thank you.
Thank you for a nice discussion, Chen. We're out of time for the first talk. Jinglong, if you want to briefly comment on the discussion, please feel free to do so, as our second speaker is setting up. Apparently, Rachitesh is already ready to go. Okay, so maybe Jinglong, any further discussion we can take it over the chat, or maybe back at the virtual venue, okay? We'll change gears a little bit, and we'll continue with single leg revenue management with advice. Rachitesh, it's great to have you here. Look forward to hearing about the work.
So much, and thank you so much to the organizers for putting together a wonderful conference. Hi, I'm Rachitesh Kumar. Today I'll be talking about single leg revenue management with advice. This is joint work with Santiago and Christian. So the traditional motivation for the problem that we look at today is the airline industry. Say you're an airline that's trying to run a flight from Amsterdam to New York, and you want to sell seats in a plane to maximize revenue. For today's presentation, let's just focus on economy seats and assume that the entire plane is in that configuration. So what exactly is the decision problem here? Like, each economy seat can be sold to different types of economy ticket holders. Okay. So on your screen right now, the three types of economy tickets sold by KLM Airlines. This is economy light, economy standard, and economy flex. These different types of tickets are called fare classes, and they differ in the amount of perks they offer to the holder. For example, economy flex will give you refundability, priority check-in, checking your bags, going through airport lines faster, things like that. And economy light is bare bones. But the important thing to note here is in the bottom of the screen, which is that all three tickets at the end of the day give you access to one seat in the economy class of the plane. So from the airline's perspective, you have this pool of economy seats that you want to efficiently sell to these three different types of fare classes. And as you might imagine, the greater the number of perks, the greater the price of the ticket. So economy flex customers bring in the most amount of revenue for the airline, and economy light the least. Now, in an ideal world, I would just sell all my economy seats as economy flex because that will get me the most amount of money, but not enough demand from economy flex might materialize, or demand for economy light might come before the demand for economy flex. The core trade-off here is, if you're faced with the customer with a lower fare class, do you sell a ticket to her, or do you protect that capacity for higher paying customers that may or may not materialize? The problem that's just described here is more general than the airline industry. More generally, what we're looking at here is a single resource unit cost resource allocation problem, where you have one resource and a limited inventory of it. Requests are arriving Sequentially, each request, if accepted, consumes 1 unit of the resource and generates a variable amount of reward. And your goal here is to maximize the cumulative reward that you can attain given your inventory. This shows up in the display ads industry, where each banner ad takes up 1 slot in the website, and the multi-secretary problem, where you're trying to hire multiple people and each person would take up 1 position in your company. But for today's talk, we're going to stick to airlines as far as terminology goes. So let me dive right in and tell you about our setup. We're going to denote the capacity of your plane. This is the number of economy seats by N. We're going to assume that the customers are arriving sequentially. Each customer belongs to a fare class, one of M possible fare classes, going from F1 to FM in increasing order. We're going to assume perfect segmentation. This is standard in the single leg revenue management literature. And it says that each customer belongs to a fare class and she's not looking to substitute between them. Upon arrival of a customer, her fare class is revealed to the airline, and the airline has to make an irrevocable accept reject decision on whether to sell to this customer or not. Selling to her leads to a revenue of FI, which is her fare class, and reduces the remaining capacity by 1 unit. We're also going to provide an algorithm that is more similar to what you might have seen in practice that airlines run, which is that we'll instead provide a menu of options to the customers and they can select their own fare class if it's available in it. This will not require information about the customer's fare class before making the accept reject decision. Finally, we allow for fractional accepts. All the algorithms we'll develop will have row rounding error whenever the number of fare classes M is much smaller than the number of the total capacity of the plane N. There's also previous work that looks at rounding fractional solutions into integral ones. Okay. So how you might go about solving this problem depends a lot on what you're assuming about the customer demand process. Work on single leg revenue management started with Littlewood in 1972. He assumed that there's a known underlying stochastic process that is generating the customers, and this led to a long line of work that makes the same assumption. The problem here is that the results require you knowing the entire customer generation process to be able to solve for the optimal policy, and most of these works also require these stochastic processes to be independent across fares. To get rid of the known process assumption, there's another line of work that assumes that there's an unknown underlying distribution which you interact with through samples. And the goal here is to get a good policy iteratively as you keep querying this sample oracle. The problem here is that all these works require stringent assumptions like low before high. That is, all the fares have to arrive in increasing order for these results to work. And also, they again need that the demand across fare classes is independent of each other. On the other extreme is the adversarial setting initiated by Ball and Queran and built on by Lan et al., who assume nothing about the demand sequence other than the fact that every customer will belong to this given set of fare classes. But this is often too pessimistic because airlines have machine learning models that they train to predict what kind of demand they'd see. So in our work, we look at interpolating between the known and adversarial settings through the framework of algorithms with advice. Advice here refers to a potentially inaccurate prediction about the future. This probably comes from an ML oracle. And our goal here is to incorporate that prediction in a robust manner into our algorithms. More precisely, our goal is twofold. One is consistency. We would like good performance when the forecast is accurate, when the advice is accurate. But we would also not like to lose our worst case guarantee. So we would like competitiveness, which is our worst case performance over all instances. Okay. So let me define a few terms and including our advice. We are going to measure the performance of algorithms as compared to the hindsight optimal solution. This is the revenue you can attain had you known the entire customer sequence upfront. Right. As you might imagine, this is a simple knapsack problem. If I give you the entire customer sequence, all you need to do is pick the top 10 fares. As far as the advice goes, this is modeling decisions, and there are many possible forms. We're going to do what is standard in the algorithms with advice framework. That is, we pick our advice to be the minimum amount of information you need in order to compute the optimal solution, which in this case is a vector A that has a tuple for that has an entry for each fare class, where AI represents the number of fares from fare class I that will become a part of your top n. So it's a prediction for what op will look like. The advantages of this is that it's oblivious to order. As long as you have AI fares from fare class Fi, they may arrive in any order, and that it's easy to learn since you're only looking at frequencies. It has low sample complexity. An example of an advice, if your capacity is 100, might be 0 fares from F1, 40 from F2 and F3, and 20 from F4. More formally, we're going to say that an instance I conforms to advice A if its top n fares are exactly what the advice is saying they'd be. So its top n fares are AI fares from class Fi. On the right, you have the advice that we just saw on the last slide. And on the left, here's an instance that conforms to this, right? Why is that? Because the top n fares are exactly 20 fares from F4, 40 from F3, and then 40 from F2 because your capacity is 100. So this instance conforms to the advice, no matter which order the customers in this instance come in. And as you can see, the instance doesn't have to conform to the advice everywhere. In case once you get out of the top 10, there may be any number of customers from lower fare classes. Okay. So now I can rigorously define our metrics. Consistency, an algorithm is called beta consistent on advice A if it attains beta fraction of the optimal revenue on every single instance that conforms to the advice. That conform is defined as we just talked about in the last slide. And competitiveness, an algorithm is called gamma competitive if it attains gamma fraction of the optimal revenue on every single instance, no matter what the advice is. This is the goal of traditional worst case online analysis, but now we also want good performance when the advice is accurate. Consistency and competitiveness are often conflicting objectives. So what we would like ideally is an algorithm that optimally trades them off. That is, we want an algorithm that can achieve performance on the entire Pareto frontier. So you give me a level of competitiveness and an advice, I'll give you the best possible consistency and achieve performance at that level. In this work, we do exactly that. We give an efficient algorithm that achieves performance on this Pareto frontier. I would like to know that we achieve this performance for every single advice. Some of the works in algorithms with advice framework that use algorithms with advice framework often try to achieve consistency, taking a worst case overall advice. In this work, we go for something much stronger, which is the Pareto frontier for every single advice. Okay. Any questions about this?
No questions in the chat.
All right. So with that, I'll dive right into our results, which is how we establish our upper bound and our optimal algorithm. So the way we'll establish our upper bound is through a collection of hard instances. Let me try to build up to that. So consider an advice A. This is again a tuple A1 to AM, where AI is your predicted number of customers from fare class Fi in your top n fares. First, an observation that any good algorithm should have a preference for higher fares. So given a history, if you're accepting a lower fare at this point, you should also accept a higher one. This in some sense means that increasing order of fares is the hardest order to tackle in terms of maximizing revenue. So if you want a hard consistency instance, that is a hard instance which conforms to the advice, we would like the largest possible instance that conforms to the advice in which fares arrive in increasing order. That is exactly what we're going to construct. More formally, let L be the smallest fare that is predicted to be a part of your top n fares. And IA is just fares arriving in increasing order in blocks of n up till fare FL, and after that it's in blocks of AI. What's important to note here is it's in increasing order, it's as big as you can make it. I mean, going beyond n becomes irrelevant, and then the highest n fares here are exactly what the advice is saying they'd be. So it conforms to advice here. What about competitiveness? Ball and Queren had already characterized what are the hardest instances when you're trying to maximize just the competitive ratio, just competitiveness. And they showed that they are just increasing order of fares in blocks of n and all their prefixes. it turns out in our setting where you're trying to go for both consistency and competitiveness, the hard instances are prefixes of the hard consistency instance IA concatenated with the prefixes of the hard worst case instance IF. What is a prefix here? It's just a truncation of an instance at a particular fair class. So IAI would be the truncation of the consistency instance IA truncated at fair class I. So IAL plus 2 would be IA truncated at FL plus 2, and IF2 would be just the worst case instance IF truncated at fair F2. So what is the intuition behind creating such hard instances? The idea here is that when an algorithm is seeing a prefix of the hard consistency instance, it has no idea whether the advice is going to come true or not. So it must always prepare for the eventuality that it might come true. So while giving her the consistency instance, we can bamboozle her in the middle of it by giving her a hard worst case instance IFJ. So the algorithm has to make sure that it's performing well on the hard worst case instance if it arrives, and allocate capacity appropriately. Another important consequence of defining these hard instances is that on these hard instances, there are many pairwise shared prefixes, and this constrains the types of decisions that online algorithms can make, because they don't see into the future, and if two hard instances share a prefix, they must share the decisions of any online algorithm. This constrains the total number of decisions to order n squared. We use all of this to write an LP that'll give us an upper bound on the best possible level of consistency you can achieve for a given level of competitiveness. So given that level, we try to maximize consistency subject to the capacity constraint. We require that the revenue from the hard consistency instance IA is at least a beta fraction of the hindsight optimum. So this is consistency. And then finally, we require the revenue on every hard instance to be a gamma fraction of the hindsight optimum. This is just on hard instances. And as I just said, the number of decision variables are also order m squared. So this entire LP is order m squared in variables and constraints. The result is that the value of this LP is an upper bound on the level of consistency that any online algorithm can achieve, subject to it also being gamma competitive. Right? And proof is simple. The decisions of any online algorithm can be converted to a feasible solution of this LP, and then you have the upper bound. Now, having described the LP, we would like to construct an algorithm that achieves performance on the upper bound given by the LP. To do that, we will use as a building block protection level policies. These are the workhorse of single leg revenue management. They have also come out of theoretical analysis of all kinds. A protection level policy is a policy parameterized by m protection levels, Q1 up to Qm, one for each fare. Your Qi represents the maximum number of customers or fare Fi or less that should be accepted. And the policy is simple. You select every customer as long as accepting her does not violate any protection level. So it's a upward closed way of accepting customers. Okay, just to make sure everyone's on board, I'm going to go through a couple of examples. Say your capacity is 3, the number of fare classes is also 3, and the protection levels are 1, 2, and 3. In the first sequence, you get F2 followed by F2, then an F1 and an F3. So in this case, you would accept the first 2 customers because no protection level is violated. You would reject the third one because accepting her would violate protection level Q2. And finally, you would accept the last customer because no protection level is violated. If I were to flip the middle 2 customers, then again, I would accept the first one, no protection level is violated. I would accept the second one, no protection level is violated. I would reject the third one because again, Q2 protection level would be violated if I accepted her. Finally, I would accept the last customer. So I'll give a high-level overview of how to go from the LP to our optimal algorithm. What our algorithm does is it solves the LP. It takes the optimal solution. It uses that to construct a set of protection levels. And then depending on whether the advice is coming through or not, it switches between these protection levels in order to attain good performance. I'll not go into the detail here due to time constraints, but the non-trivial part here is how do you switch between the protection levels? More concretely, our result is that the algorithm that I just outlined is gamma competitive and beta consistent on advice A, where beta is the value of the LP. And since the LP was an upper bound, this algorithm is in fact optimal. In proof, we use the optimal solution of the LP to construct protection levels that perform well on the hard instances. And then we show that good performance of the hard instance translates to good performance in every other instance. This is the sense in which I meant that those instances are the hardest. Okay. So I just called protection level policy the bedrock of single leg revenue management and said all kinds of good things about it. It also has many good practical properties that are not captured by the model. But now I've just given you an algorithm that is not protection level policy. So how much are you losing by making that switch in the optimal algorithm between two protection levels? That no longer makes it a protection level policy. So we wanted to find out what's the best performance you can achieve if you just restrict yourself to the class of protection level policies. Just a quick recap of protection level policy, again, parameterized by M protection levels, one for each fare. QI here is the maximum number of customers of fare FI or less that should be accepted. But I'll give you an alternative implementation. This is what you might have seen on actual airline websites. You start with all fares open. And every time a customer arrives, if her fare class is available in the open fare, she buys a ticket, otherwise she leaves. And anytime during this process, if you hit a protection level QI, you close all fares FI and below. So this will run exactly like the previously described protection level policy. The advantage here is that you don't need to know what the fare class of the current customer is. And also it satisfies monotonicity. You will never accept a customer having rejected a customer of the same fare class before, which can lead to game theoretic issues in practice where customers might try to game your algorithm. So what we want to do here is find the best protection levels that optimally trade off consistency and competitiveness. More concretely, we develop an algorithm which for every advice in a given level of competitiveness gamma finds protection levels that have the best possible level of consistency among the class of all protection level policies that are gamma competitive. And the way we do this is we first pose the question as that of a search. So given an advice, say consistency level beta and competitiveness gamma, we like to answer the question, can you attain beta and gamma using any protection level policy? If I can answer this question, then I can do a grid search or a binary search to compute the Pareto frontier for protection level policies. Turns out answering this question directly is a bit tough. So what we do is we reframe the question as that of minimizing capacity needed to achieve this level of consistency and competitiveness. And that question we answer through a greedy algorithm that iterates over fares. And at each stage, it sets the protection level QI to be the minimum amount that you need to accept at that stage to remain gamma competitive and beta consistent. And then if the final amount that you picked is less than n, you can achieve it, otherwise you can't. And then we perform a binary search using the subroutine to find the Pareto frontier and the best protection levels. The main result here is that this simple greedy procedure does in fact compute the optimal protection levels. And we couldn't do this through an LP because the behavior of protection levels is nonlinear and non-convex. So now I've described these two procedures. We can find the best protection level policy and the best policy overall. How do they compare? And that's what we investigate in our numerical experiments. As you can see, on most types of advice, we find that the optimal protection level policy is in fact optimal in general. There are some types of advice where the monotonicity property fails for our optimal algorithm, but it achieves better performance. So it's not without loss the monotonicity property that protection level policy enjoys. Also, another important fact that we found out was that you can gain a lot in consistency for a small loss in competitiveness and vice versa. So if you're willing to sacrifice a little bit of consistency, good performance on your advice, you can gain a lot in robustness. In conclusion, we gave an efficient algorithm that is optimal for every single advice. This is stronger than some of the previous works that only try to do it in the worst case over advice. We gave an efficient greedy algorithm that computes the optimal protection level policy for every advice. In the future, we would like to be able to incorporate dynamically changing advice. This has some modeling challenges. So right now, we're only assuming that advice is given at the beginning of the time horizon about all future demand, but this might evolve as the environment is changing. But it's not exactly clear how to model that efficiently. And we would also like to extend our results beyond just a single resource to network revenue management. Finally, we would like to note that this algorithms with advice framework is trending in the computer science literature, and with good reason. It is part of their move beyond worst case analysis, and it allows them to harness the power of ML predictions in a robust way. The RM community also does a lot of robust analysis, and this is an interesting framework that we think has lots of potential applications in revenue management. Thank you for your time.
Thanks so much, Rachitesh. So we have time for a couple of quick questions. While you were presenting, there was actually a quick question in the chat. Santiago answered this question already, but I don't know if you also want to comment on it for everyone else in the audience.
Yes, I'll just repeat what Santiago said. So we look at robustness. We give a variant of our optimal algorithm that is robust to deviations from the advice in a smooth way. And we also characterize the robustness in the sense that Jerry is asking, which is performance away from the advice for our optimal protection level policy. And then we also run numerical experiments with our original optimal algorithm and how it behaves under perturbations of the advice. Punchline here is it performs better than the ball and query N1, even if your coefficient of variation is like 50 or 70. So something to be gained even if you have bad advice.
And one quick question. I know you mentioned it in the future directions, but the network revenue management direction sounds super interesting as well. How would you think about advice there? And do you have any conjectures or thoughts about how the analysis would unfold?
Yeah, advise that if you have finitely many types, then you can again maybe do frequency, but there even worst case performance guarantees. The adversarial setting, you can't get a guarantee if you're not putting constraints on what kind of rewards and consumptions you have. So you might have to make more assumptions. Also, there's been a work for the other name that tries to initiate matching algorithms with the optimal dual solution that they learn in the Hungarian algorithm, and that's similar. So the advice here is the dual, but again, I don't know if any work, but something similar. Basically, something that you can learn with low sample complexity, and it gives you information about the optimal.
Thank you.
Hi, I have a question. Sorry, can I ask a question?
Yes, Phil, go ahead.
So you said you can derive the optimal trade-off for any given advice. Can you speak a bit about, like, given a set of fair classes in N, what types of advice lead to the worst trade-off?
Right. Worst trade-off in this. Okay, so you want the minimum consistency when you're going for the highest competitiveness?
Yeah. So like if you fix the set of fair classes and fix N, the best possible competitiveness is fixed, right? But you're saying, like, depending on sort of how extreme the advice is, like intuitively, the more extreme the advice is, the faster consistency should deteriorate.
Yes, you're right. So if you take the ball and query solution, and then you see how close advice is to that, that's kind of a good metric that I use to guess if the advice is going to perform, like what the trade-off's going to be. So if you're going for robustness and you're already performing well, then you're going to get good consistency, if that makes sense. So if you forget about advice for a second and just compute the worst case protection levels, if your advice is close to that, or if those protection levels perform well in the advice, then you would do well in robustness with very tiny loss.
Got it. Okay. No, very interesting. I was just curious, sort of like, what are the types of advice that give you sort of the the lowest trade-off between competitiveness and consistency. Thanks.
Yeah, so also, Rachitesh, can you explain like qualitatively what's the structure of the BQ worst case instance so that they...
So it's, you mean the IF one?
Yeah, so then, yeah, so that's kind of the worst that it can look like, essentially.
Yeah, so yeah, that's the BQ worst case instances are the ones where you're trying to maximize competitiveness. If your advice, if the whatever protection levels you compute for the worst case, if those protection levels perform well on the advice, you'll get good consistency for free, essentially.
So thank you, Rachitesh. In the interest of time, let's continue with the discussion. Thanks for stopping the screen share. Our discussant is William Cooper. William, if you can share your screen.
Yep, okay. How's that?
I can see it clearly. William, thank you for discussing this paper. I look forward to the discussion. The floor is yours.
All right, thanks. Hey, let's see. So first off, thank you, Rachitesh and Santiago and Christian for the interesting paper, and thank you, Rachitesh, for the interesting talk. So I liked it a lot. My name is Bill Cooper. I'm the discussant here. So I just start by giving out or summarizing what I sort of think are the main points of the work, and then at the end maybe talk just a little bit about you know, opportunities, future directions, things like that. So, whoops, let's see, I need to be able to move forward. Okay, there we go. Okay, so the basic setup of the problem is a single leg revenue management problem. So this is one that's been around for quite a long time. And there's N seats on the flight, and there's M fare classes. They're ordered so that fare 1 is the lowest fare, and fare M is the highest fare. And a traditional approach to this problem, sometimes called independent demand model, would assume to start by putting some distributions on the number of customers that want each type of fare. And then it would try to maximize the expected sales revenue from selling the N seats. And I guess independent has a few different meanings there. So one is often that the amount of demand for each fare is independent of the amount of demand for each other kind of fare. So that's one way the word independent is used. And then it's also sometimes used to emphasize that that what a customer wants is exogenous to what's being offered to that customer. So I'm a customer who shows up, I have a specific fare class in mind, I will buy that one and no other one. So this paper, this talk, it keeps that exogenous demand assumption, but it drops any assumptions about distributions of demand, for instance. So there's no probability distributions on what customers are going to show up or what order they're going to show up in. So the basic setup is like this. Again, sort of the high level point is that we're getting rid of any distributional assumptions on how many customers show up or what order they're coming in. And so the sort of the basic starting point is what's called an instance. And so an instance is just a sequence of customers who come to buy tickets or buy a ticket. And so the SI, this is going to be the fare that the ith arriving customer wants to buy. And again, there's no assumptions about the distribution of I either. And so if I'm the airline and I'm a clairvoyant airline, then I will look at what I will see what instance I have. I will know the instance in advance, and the amount of revenue I get, that will be called opt of I. And the way you could figure this out, right, is you you start and you fill up as much space as possible with customers who want to buy the most expensive fare. And then after that, you fill up as much space as possible with the customers who want to buy the next most expensive fare. And you keep on doing that until you've sold all your seats. And that would give you opt-I. And again, this presumes that I, as the airline, know what the instance is. As a practical matter, we would not know what it is. We would start to learn about it as we see the sequence of customers arriving. But we wouldn't know the instance until after the problem was over, the full instance at least. So that's the basic setup. And so a few papers have looked at this kind of problem from the viewpoint of competitive analysis of algorithms. And the idea there is the following. So let's suppose we have a policy, or policy, you can think of it also as algorithm, I think is the term that was used more in the paper. But let's suppose we have a policy. This is just going to tell us which customers to accept, which ones to turn down. And it has to work dynamically, so I can't look into the future with this policy. It could also be randomized if I wanted it to be. I'm not going to go into any detail on that, but that's allowed. And so if I decide to follow policy P and instance turns out to be I, then the revenue I get, again, this could be expected revenue, it's a randomized policy, is RP of I. And so then the idea is to look at the competitive ratio of a particular policy. And so what I would do then is I would look at my policy for a given instance. I would figure out what revenue it's going to give me for that instance. I would divide that by the optimal revenue for that instance. Again, that optimal revenue is for the clairvoyant. And then I would minimize that over I. So that's giving this particular policy I'm looking at, it's finding in some sense the worst instance for this policy, where worst is being measured relative to the clairvoyant optimal. So after I do that for each I, then I would maximize over policies. And so this approach has been used before. And so the novel aspect of this work, the work that was just presented, is to ask the question, well, what if there's a prediction about what the instance is? Okay, so up until now, we're just assuming it could be any instance, and you don't know anything about what it might be. So what if there's a prediction for what the instance will be? And you could think of a prediction as in some sense like a forecast to some extent, I guess. And so the way the authors have very cleverly factored this prediction in is through what's called an advice. And so what an advice tells us is it tells us for each fare class, so for each customer class, it's going to tell me among the top N fares that show up, how many of those are in fare class I. And if you have this information, this advice, then that's enough to compute the clairvoyant optimal if the advice is actually correct. Okay, so if the advice is right, then the advice tells you everything you need to know to compute the clairvoyant optimal. Of course, the issue may be that the advice may or may not be correct, and that's one of the essential points of the work, is to consider trade-offs. You want to make sure you have good performance when the advice is correct, but you also don't want to put all of your eggs in that basket in some sense. You also want to make sure, or ensure to the extent possible, that you get reasonably good performance if the advice actually is not correct. We'll say in coming up in a slide what more precisely what is meant by correct. So let's move on to the next slide here. So a key idea in the paper is what does it mean to conform? What does it mean for an instance to conform to the advice? And so this basically just means that the instance is consistent with the advice. So in other words, if you follow the policy that the clairvoyant thinks would be the optimal for the advice, then that will also give you the optimal for the instance. So that's a consequence of the instance conforming to the advice. Again, at a high level, it just means the advice is right. And then the basic things that are being traded off in the paper are the notions of consistency and competitiveness. And so a policy is called beta consistent for the advice if its revenue, when I apply it to instances that conform to the advice, is at least beta times the clairvoyant optimal. So that's beta consistent. So this is basically saying that the policy works well when the advice is right. And then the other notion is gamma competitive, and gamma competitive is essentially saying that if I get this advice and I get an instance and I apply my policy using those or to that instance using that advice, then it will be at least gamma times the optimal. And here I'm not just looking at instances that conform to A. Again, conforming means that the advice is right, but I'm looking at any instance. So this is looking at considering the possibility the advice is wrong, conceivably way off, or possibly not off by that much, but not correct. So this is the basic trade-off that's under consideration. And the sort of, in some sense, the central result of the work is to come up with a way for obtaining the Pareto frontier between consistency and competitiveness. And so the way this is done is the authors introduce this set P of gamma. This is the set of gamma competitive policies. And then beta A of gamma, what is this telling us? So this is for a particular level of competitiveness and a particular advice. This is giving me, so first I'm going to figure for any particular instance, for any particular policy, I'm going to figure out how well does it do relative to the clairvoyant optimal on that instance. And then I'm going to maximize overall policies in the set of gamma competitive policies. So this is giving me, in some sense, for a particular value of gamma, gamma competitiveness, it's giving me the best level of consistency for this particular advice. And a main result of the paper is a linear program to compute that beta. And there's sort of two essential pieces to this. So the first piece is that there's an LP that computes an upper bound on this beta of A comma gamma. And then the solution to that LP is used to create a policy that actually attains that upper bound. And so then that tells you that the solution to that LP is exactly giving us beta of A gamma. And then this frontier that we're interested in is the gamma beta pairs. So that's sort of, I would say, the central result of the paper. If I could sort of say what are the sort of the essential points here and main contributions. So one is a very novel viewpoint that introduces predictions or advice into competitive analysis of algorithms for this sort of canonical revenue management problem. And this central result I just mentioned was the linear program that allows computation of this Pareto frontier and also provides a policy. And there's several extensions to this that are also mentioned in the paper. So one is some method that incorporates some, you can think of it as robustness. So it allows settings where you're not looking just at cases where the advice is exactly correct, but almost correct in some sense. And then there's also some analysis where where there's a restriction of what policies can be considered only to protection level policies. And I'd say that's quite a bit of interest, since those are very standard kind of policies or a form of policies to use in revenue management problems. So I have one slide here to go in 1 minute. Let's see. So in terms of opportunities for moving forward, so I guess one question that might come up is, so I guess in sort of traditional versions of this problem, sort of going back to the sort of very original work, the starting point is demand distributions, and those are forecasts of demand distributions. So one question would be is that if I have a forecast of demand distributions, what advice is that providing me? So that's a question that sort of you might want to think about. Another thing that might be interesting to look at would be forecasts or advice that come from multiple sources. So, you know, the sort of the one advice, or one source of advice might be a system generated advice. Again, this could be thought of as a forecast, but there also might be users. You know, there's revenue managers who use revenue management systems, and they have their own ideas of what may happen. So those people may produce advice or forecasts, and you might have, I don't know, a blend of the advices, or maybe some sort of hierarchy of advices. So it might be a more complicated frontier in that case. And then another thought was to look at consumer choice models, or more sophisticated models of how customers act, sort of moving beyond the independent demand model. So that's what I have. Again, a very interesting paper. I enjoyed reading it, so thank you very much for that. And I'll turn it back over now.
Thanks so much, Bill. Rachitesh, I don't know if you want to comment on anything you heard. If not, that's also fine.
Thank you so much, Bill, for the great discussion. The demand distributions, we did think about it, but we haven't been able to nail down a method of how you evolve that advice as you start seeing customers, if it's distributional. The forecast and multiple advice at the same time, we did not think about. So thank you for pointing that out. And then, yeah, that's another next step, looking at customer choice and assortment. Thank you so much.
Thank you.
Sounds like it's the direction. It's a lot of interesting future questions. I would like to thank all of you for attending this session, and I also would like to thank Jinglong, Chen, Rachitesh, and Bill for the talks and discussions. I learned a lot in this session. This concludes the day, and we'll continue tomorrow at 8:40 Central Time. Good evening, everyone.
Thank you. Thank you, Bill.
Thanks.